Assalamu alaikum. So in our last lecture, we have discussed about different inversions. So uh, the last discussion we had the inversion of slider crank mechanism. So it was a single slider crank mechanism. So so within this one, there were one of the inversion was pendulum pump or pull engine, basically the two cylinders assembly. Then we had another one oscillating cylinder, so where the cylinder was oscillating about some reference position. And the third category, the rotary internal combustion engine, and where we have seen one of the example as well to express how the rotary engine does work actually. Uh, yeah. So this was the third category, the inversion of slider crank mechanism. And then the fourth one is quite interesting, where we have the crank and slotted lever quick return motion mechanism. So crank and slotted lever. So you got here, for example, one of the slider, which is as a link one. So this one big bar, and you got a crank which is a link 2 which is moving in a circular motion. So this is the crank, and which is linked with a connecting rod. So this is the connecting rod, and which helps moving this ram. This ramming process, which is like one of the cutting stroke, return stroke. So this is line of the stroke. So this slider, so because this is the category we are in of the slider crank mechanism, so this slider moves to and fro. So this moves to and fro, and this is helped. This such mechanism are quite widely used for the cutting. So that's why this tool here, which is basically a shaping tool, like a shaping tool. So this moves up and forward and reverse. So this helps in cutting basically. So it goes slowly in the forward stroke and returns is quite slow stroke. So it's a quick return mechanism basically. So we got a crank and slotted lever with a quick return motion here. So let's look go through this. So this mechanism is mostly used in shaping machine. So in your machine workshops, you would have learned about different mechanisms or different machines, and shaping is the one which helps to cut, basically remove the material. So it goes to and fro motion, and which cuts the material from with this tool, cutting tool basically. So in this mechanism, the link AC, so the link AC, so this link A and this is C up here, forming the turning pair is fixed. So this is a fixed. That's why you got this small lines here. The link 3 corresponds to connecting rod of reciprocating steam engine. So this is the same link. So the fixed link is 3. So this is representing the connecting rod of a reciprocating steam engine. The driving crank. So this is the crank, which is a link 2. CB. So this is the CB. So this is length. So basically, two positions are shown. So this is the B. This is B, and this is C. So this is the CB is a crank. At two positions, it could be CB1 or CB2. Basically, these two are the positions, different positions. CB revolves with uniform angular speed about the fixed center C. So this CB is revolving around a fixed center C. A sliding block attached to the crank. So this is the sliding block. So this is link 1. This is the sliding block. You just imagine when it's moving. So this sliding block is just sliding on this length AC basically. Sliding block attached to the crank at B. This is a B. Slides along the slotted bar. So this is the slotted bar. So this slotted bar AP. So you see the long one is the slotted bar. So let me show you this one. So this AP from here to this one AP. So this is the slotted bar. That's why we have the name this slotted lever basically. AP and thus cause AP to oscillate about a pivot point A. Now, if you try to understand what is happening, so CB is rotating. So this is rotating like this. So when it's rotating, this is causing the oscillation of this B. So when it's oscillating, so of course it is helping to oscillate. So this P is basically oscillating from P1 point to P2 point. So this is like the extreme position of this slotted lever. A short link PR. So this is a short link. So this is one of the link connecting toward. This is toward basically connecting toward. This is short link PR. Transmit the motion from AP. So from AP, it transmitted motion to this position to the RAM. AP to RAM, which carries the tool and reciprocates along the line of stroke R1 and R2. So this P is basically going yeah. Yeah. So the point P is reciprocating from P1 to P2, and of course the connecting toward basically which is connecting PR to the RAM. So RAM will oscillate from R1 to R2. So that's also line of stroke. The line of stroke of the RAM R1 R2 is perpendicular to AC. So we got this AC. So this AC, the length, basically this R1, R2 is a perpendicular to that. So this is line of action of AC basically. So that's the explanation for this mechanism. Let me maybe we'll have some more on the next slide. Yeah. So now again, in the extreme positions AP1, so this is the extreme position AP1 and AP2 are the extreme positions basically. AP1 and AP2 are tangential to the circle. So you see they are tangential to this circle. So this is the tangential. So this length, there's the circle itself is a tangent to this line. And the cutting tool is at the end of the stroke. So we got at the end of the stroke, we got the cutting tool basically. So this one, ram, it has end of the hair, we got the cutting stroke. The forward and or cutting stroke. So the forward is basically the cutting stroke occurs when the crank rotates from position CB1 to CB2. This is important point actually. So from P1 to P2 or of course from R1 to R2 is the cutting stroke, and during this movement crank is moving. So now the crank is covering this much distance from CB1 to CB2. So it is of course moving in this direction as well. So you see it is covering quite larger angle when the crank rotates from CB1. So this is CB1 position, this is CB2 position. So it is moving from CB1 to CB2, and of course the link P moves from P1 to P2, and then the RAM itself is moving from R1 to R2. So or angle through an angle beta. So we are covering angle beta basically during this process, right? Uh, in a clockwise direction. So it's moving in a clockwise direction. The return stroke occurs when the crank rotates from position CB2 to CB2. So now Of course it has to come back because the crank keep continue moving. So crank is continuously moving. Now crank is again further does another cycle. So it moves from CB2 to CB1, covering an angle of alpha through an angle of alpha in a clockwise direction. Since the crank has a uniform angular speed, so therefore, so this is that's what it makes a quick return mechanism. That's what we have studied already in previous examples, the quick return mechanism. So in a way forward, the angle is covered as a beta, which is larger, you can just see. And on the way back, the crank is moving from CB2 to CB1. And of course, the RAM or the point P is coming back from P2 to P1. And the RAM is coming from R2 to R, which is called as a return stroke. So again, in the forward stroke, beta angle is covered. On the return stroke, alpha angle is covered. Do not confuse yourself uh, with the alpha and beta basically, because it doesn't matter whatever angle you take. If you take alpha forward or beta forward is fine. But the important thing is here, the larger angle is covered for the forward stroke and smaller angle is covered for the return stroke. And that what it makes a quick return mechanism. So that's why this is called quick return motion mechanism also, because we are quickly coming back covering same distance but now doing quickly. So that's why it's a quick return. And the crank and slotted lever is because we have the slotted lever. So this lever is slotted, so that's why. All right, so if you consider time of cutting stroke and time of return stroke. So time of cutting stroke, beta is being covered, and in the return, alpha is covered. So beta is beta, but alpha, total is 360. So you can write as a 360 minus beta. Or of course, you can write this one as like that. So beta, because beta is 360 minus alpha and 360 minus beta is alpha. So basically you can calculate the ratio of cutting stroke to return stroke. This is called as a time ratio as well. Time ratio. We will use some problems and then you will use over there. So it is called as a time ratio as well. So time ratio can be determined by just taking the angle of basically the ratio of the angles. All right. So then a little bit further formulas basically. Since the tool travels a distance R1R, so this tool is traveling distance from R1 to R2 during cutting and return stroke, therefore the travel of the tool or length of the stroke. So now we just try to find out the length of the stroke from here to here. So R1, R2, which is also equal to P1, P2. So you just imagine, because it has to cover distance from P1 to P2. So R1 and R2 is equal to P1 and P2. So which is also equal to 2 times P1Q. So what is P1Q? P1Q from here to here. So this is 2 times of 21PQ. So, and now if you look at it in a triangular method, so if you just consider this triangle, yeah, so if you just now make this triangle, so this angle is basically 90 minus alpha. Why 90 minus alpha? Because this is 90. This is total angle is alpha. So, and this angle is alpha by 2. Alpha by 2. So I will just draw again this triangle here. So you got like that basically. So this angle is alpha by 2. So this angle is alpha by 2. And we have already discussed this is perpendicular. So this is perpendicular. This is 90. So this angle would be basically 90 minus alpha by 2. This angle. So this small angle over here. This is 90 minus alpha by 2. So now if you consider this big triangle, again, I will draw it. This one. So this one, this is like P1. This is Q. And this is 90 minus alpha. 90 minus alpha by 2. Alpha by 2. So what happens? This one you can use as a, so we are interested in this length. So 2P1Q should be equal to 2. So sorry, this one is A. So this length, so you know, whenever you want to solve the triangle, so this is cos component, this is sine component. So that's what we are writing. So AP1, so this is AP1. You take sine of the angle, which is this one angle, P1AQ. You know, this nomenclature, angle P1AQ is basically this angle. P1AQ is this angle, and AP1 sine angle of P1AQ. All right, so uh, so this is the angle. This is the angle 2AP1, and P1AQ is 90 minus alpha by 2. So you just plug in the angle value. And of course, when sine 90 degree minus alpha by 2, you will have 2AP. So this will become cos alpha by 2, right? So yeah, so one more thing is AP1 is written as a AP because AP1 and AP2 are same thing actually, because P is the point basically where the length is basically. So you can write it as AP. And now cos alpha by 2. So again, so we got this triangle. You got this triangle. So you got this is B1. This is B1, and we got this is C, and then this is A. And we got this one as a 90 minus alpha by 2, and this is alpha by 2. So this is alpha by 2. And this is 90 degree basically. So now you can imagine this one basically cos alpha should be here. So yeah, so cos alpha should be alpha by 2 should be yeah, so cos alpha should be, because this is the base, so this is CB1, and this is the longer side, which is in front of 90 degrees, so we got AC. So that's why we got this conversion here. And now because yeah, so you CB1 and CB2 are basically the same lengths, because B is the maximum point, so you can just write CB. So that's what he's writing. So instead of CB1, you're writing CB actually. So now this is the basically if you write on the right side, so this is RR1. So this is RR1 basically. RR1 or PP1. RR1 we are writing because this is the physically important parameter which is we are interested in actually. So that's what we can say RR1 during cutting and return stroke, therefore the travel of the tool. So this is tool travel or travel of the tool, or you can call as a length of the stroke, which can be determined but just by using these formula. So what is this formula? AP is the length, which is this length, which is the slotted lever length. So you know that CB is basically the crack length, and AC is the frame. So this is this length. So you just need to know these lengths. You can find out what will be your length of stroke here. All right. And yeah, so next category is different. So we will have some problems solving from here after discussing this one. So inside, so Whitworth quick return motion mechanism. So here actually, what's happening? So this mechanism is mostly used in shaping and slotting mechanism. So you see the previous example, which was the crank and slotted lever quick return mechanism. This is definitely for shaping machine. So the shaping is basically when you want to remove material from some part. So you can just look at the any animation available or video available, or you can read about the shaper machine basically, which requires for the cutting of the material, removing of the material. So the next one is Whitworth quick return motion mechanism, which is also for the shaping and slotting machines basically. So what is it in this mechanism? Link CD. So we got link CD. So this one, this small length here, CD, which is also called as a fixed. So this is link 2. Forming the turning pair is fixed as shown in figure. The link 2 corresponds to crank in a reciprocating engine. So you see now this is the inversion of slider crank where we are fixing the crank of the reciprocating system. But now we just go back to, so here this AC was AC basically the link 3 crossfire to connecting rod, the link 3. So you see this link 3 was a connecting rod. So this is a connecting rod being fixed in this crank and slotted lever. But now we are fixing the crank. So this crank is fixed basically. So the driving crank CA, the driving crank CA, yeah, so this length. Yeah, so driving crank. So this is the driving crank. CA is a driving crank. Rotates at uniform angular speed. So this one, CA rotates at uniform angular speed. The slider link 4 attached to the crank pin at A. So this slider, which is this one, this little assembly, the slider link 4 attached to the crank pin at A slides along the slotted bar PA. So we got this bar, this is hole is bar, and where the slider is just sliding across this link 1, which oscillates at pivoted point D. So, and this slider is rotating or pivoting as point D basically. So you see there are two different things. One, this is driving crank, which is moving across C. And then this slotted, the one which is basically moving across B. Oh, sorry, D. So there are two different center points basically. The connecting rod PR carries the ram. So the connecting rod, this PR from here to here, and this is carrying a ram. This is the ram to which a cutting tool is fixed. The motion of the tool is constrained along the line RD. So we always keep in a one constant line. So this one RD is the line where the cutting stroke would happen. So basically this is the cutting, the stroke length direction basically. Along a line passing through D and perpendicular to C. So this line, this is the line where the cutting stroke will, this is perpendicular to this line. And yeah, this is perpendicular to CD and passing through D basically. So that's the explanation we need for this mechanism. All right, so
further explanation now. Uh, when the driving crank CA, so the driving crank CA, this one, moves from position CA1 to CA2. So we got two positions. So CA1, this is the first position, and this is the CA2, the second position. You see there are two circles. One because of this driving crank, and another one because of this slotted, basically, which is like this circle. So it's moving from CA1 to CA2, or the link DP. So this is for the driving crank. So the crank is moving from CA1. If I draw it like this, so this is a mechanism. So CA1 to CA2. So this is the direction of movement, basically, when crank is moving from CA1 to CA2 through an angle alpha. So this is now the angle alpha. So this is what is written here, alpha as well. In a clockwise direction, the tool moves from left hand end of a stroke to right hand end through distance of 2 pd. So during this movement, the the tool moves from this one particular position. Uh, so tool moves from yeah. So tool moves from left to right, basically. P yeah, for this position, which is a cutting stroke, basically, and it moves a right hand through a distance of 2 pd. So 2 pd is a distance which is being covered. So this pd is the radius for this slotted lever to move. So when it's moving, so of course it's moving two times, basically two times of pd. Now when the driving crank moves from position ca2 to CA1. So now is this one. So the next step is this one, CA2 to CA1. So covering the link, the angle beta, basically. And of course, the link DP from DP2 to DP1. So from DP2 to DP1, basically. So you see, yeah, so this distance been covered by this slotted lever, basically, in a clockwise direction. The tool moves back from right hand end. So basically DP2 to DP1. So the tool moves backward, basically. So that's why we call it as a return stroke to the left hand. Yeah. So a little consideration will show that the time taken. All right. So So a little consideration will show that the time taken during the left to right movement of the ram during the forward or cutting stroke, so when it's moving from left to right in the cutting stroke, will be equal to the time taken by the driving crank to move from CA1 to CA2. So this time from moving from left to right for this ram, which is the cutting tool, basically the cutting stroke, is equal to the time taken by the driving crank to move angle from this to this to cover angle alpha. Similarly, the time taken during the right to left movement when it's coming back now. So this is coming back now. Movement, the ram, or during the idle or return stroke will be equal to the time taken by the driving crank to move from CA2 to CA1. So now this is the, so same thing is being explained. But so the return is beta and forward is a alpha, basically. Since the crank link CA rotates at uniform angular velocity, therefore time taken during the cutting stroke or forward stroke is more than time taken during the return stroke. So again, this is a quick return mechanism. So the time taken by the forward stroke is more than the return stroke. So in other words, the mean speed of ram during cutting stroke is less than the mean speed during the return stroke. So the mean speed during the cutting stroke. So if it's moving at constant angular velocity, cutting stroke, the forward stroke has to cover larger distance. So, the velocity is basically
distance over time. This isn't really a great example here, but because I want to relate with time. So now the distance is larger in angular. So alpha is larger, and so instead of dt over if I write alpha basically, so alpha is larger, velocity is constant. So another velocity is when we have beta over time. Yeah. So during alpha, which is larger, but beta is smaller. So the time will be taken here will be less. So that's what he's saying. The mean speed of the ram during cutting stroke is less, and the mean speed during the return stroke is more. Yeah. So it goes slowly forward, but in reverse it comes faster actually. The ratio between the time taken during the cutting and return stroke. So this is the time ratio again. So time of cutting stroke and time of return. So you see this is like alpha over beta. So now you see the time taken for forward is taken as alpha, and which is opposite to the previous example. So you just make sure you understand quite well, because when during the assessment it's not necessary what you take, if you take alpha or beta, but the important thing is you need to define it, what is a forward and what is a return. So the ratio time ratio always remains like this. So alpha over beta means the forward one and the reverse one at the bottom, and this is the ratio. So you can write in terms of alpha, or you can write this. So if you know one of the angle, you can just find out the time ratio basically. That's what these two equations mean, because the sum of alpha and beta is 360. So if you know one of the angle, you can work out what's the another angle, and then you can just find out what will be the time ratio. All right, so this is one of the example, very first example, relatively easier. Yeah, so during this example, what it says, so a crank and a slotted lever mechanism used in a shaper machine. So this is the shaper machine is one you require to cut the material. Has a center distance of 300 millimeter. Yeah. So you got center to center distance, this one, 300 millimeter between the center of oscillation and the slotted lever. So between the center of oscillation and the slotted lever, and the center of rotation of the crank. Yeah, so this is center of rotation of the crank, and this is center of rotation of the slotted lever. So that was the distance, 300 millimeter. The radius of the crank is 120 millimeter. So this is the one, the radius of crank from here to here, this is 120. This is also given. CB1 or CB2 is the same thing actually. Find the ratio of the time of cutting to the time to the time return stroke. So basically time ratio, that's what you have to determine. So we go same way. The sine of CAB. So you see the angle CAB1. So CA, this is A, B1. So this angle is alpha by 2. You know why? Because this whole angle is alpha by 2. And in the one example we studied, this was a beta. So this is alpha. So if you do it half, so it's alpha by 2. So sine of angle CAB1 basically, yeah, so sorry, so sine, it's not the CAB, so this is alpha by 2. We are solving with respect to this angle. So if this is alpha by 2, this is 90, so this is 90 minus alpha by 2. So when you write the angle, so the center one represents the angle. So this is the angle here. So CAB1 is this one. So sine of 90 degree minus alpha by 2, which is basically, you if you solve this triangle, if I write in this way, for example, to make it easier, actually easier to follow. So this is 90 degree, which is of course the B1, and you got this is A, this is 90 minus alpha by 2, and this is alpha by 2, and this is C. So now you can easily solve it actually. So you got sine of this angle, which is 90 minus alpha by 2, should be equal to this length, which is CB1. Yeah, this is B1 over this length. This is length. So this is AC. So both lengths are given. Yeah. So we got CB1 and AC1. So CB1 is 120 and AC is given 300. So you just plug in numbers. So that's what the sine of angle is being there. And once you know this sine of this one, CAB1, so you can work out backward to find out the angle. So again, you plug this 0.4 over here. So this 0.4 you plug in over here. So that's what we are doing. So then, of course, let me clear it and then. All right. So now, because what we are doing is, yeah. So you just plug in here 0.4, right? So 0.4 is equal to sine of 90 minus alpha by 2. Yeah. And then you just bring over here. So it's a sine inverse of 0.4. And so that's what we are taking, the sine of the angle. Yeah, sine inverse of 0.4 when it goes over there. So it is 23.6. So now we are left with 90 minus alpha by 2, which is like you bring this 23.4 over there, which is minus, and then you multiply with alpha to find out the angle basically. So once you know your alpha, it's very straightforward. You just plug in the for the time of cutting stroke over time of return stroke with the equation. So you work out your alpha. So you got like just numbers and find this is the time ratio. So basically this time ratio, what does it mean? This time taken by cutting stroke is 1.72 times more than for the returning stroke. That was this conclusion is. So we'll continue with this one with the second example in the next lecture. Yeah, so that's it.